Thank you, Mr. Chairman, Professor Yoshida. Dear everyone, good afternoon. My name is Jun Gao. My supervisor, haikun zhao, didn't get his visa, so sorry not for attending this meeting. Today, I will report his presentation. The topic is counterbalancing impacts from historical anthropogenic azoles and greenhouse gases on global scale tropical cyclone genesis. I will give this talk into the 5 parts. First, let's move to the part 1, give a brief introduction. As we know, under global warming, extreme weathers and climate events are become more frequent. Studies have shown that TC intensity, TC rainfall, and the accompanying storm surges are projected to increase with anthropogenic force-induced global warming. However, TC projections, various models, and the reliable TC records are short. So whether anthropogenic forces have yet affected TC futures and how will change future TC frequency over the global is remaining conclusive. One of the main obstacles is the lack of understanding of how individual anthropogenic forcing alters TC activity. Up to date, current studies mainly focus on the GHG impacts. Recent studies have suggested that the AA forcing has a significant impact on basin scale TCs. For example, it has a significant impact on the recent decrease of Western North Pacific tropical cyclones, as well as the significant impact on the North Atlantic storms. However, what's the response of the global scale TCs to AA forcing is unclear. So here we mainly focus on the 2 following questions. The first one, what's the response of the global scale TCG to AA forcing and associated mechanism? And the second question, what's the role of AA and GHG2 forcings in shaping global TC scale, global scale TCG pattern? To identify how AA and GHG forcing impacts global TCs, we selected 14 CMAP6 models, monthly outputs of 4 experiments: historical aerosol only, historical GHG only, and pre-industrial simulations. In the table, we can see that the ensemble mean of historical aerosol radiative forcing is minus 1.14 watt per square meter, much smaller than that from GHG forcing, and consistent well with the changes of tropic and global and tropic mean SST, respectively. These 2 GPIs are Genesis Potential Index GPIs are used as a good proxy representations. The first GPI is developed by the Professor Kerry Emanuel, and the second is from Wang and Murakami. And from this figure, as shown in the figure, these 2 GPIs can both well simulated TCG climatology over the globe. This slide shows the influences of anthropogenic forcing. And these 2 GPIs both consistent show the hemispherically asymmetric TCG pattern, with an overall North Hemisphere decrease and South Hemisphere increase. Is in the figure. And in ENGPI, we can see almost simulated the reduced TCF in the North Hemisphere, and 11 out of 13 models simulated the increased TCF in the South Hemisphere. And in DGPI, 11 out of 3 models simulated the reduced North Hemisphere TCs, and all models simulated the increased TCs in the South Hemisphere. It is found that changes of large-scale environmental factors are responsible for the asymmetric TCG patterns. And the vertical wind shear, mid-level moisture, and the 500 hectopascal vertical pressure vorticity consistently shows a hemispherically asymmetric response under AA forcing. And relative importance of each factor also support it. But we need to notice that the MPI and 500 hectopascal meridional wind shear vorticity choose the minor role in represent the extremic TCG pattern. Also, the changes in the zonal mean circulation are further examined. The shading is the climatological mean up motion. We can see an obvious decrease at TCZ and the regional headly circulation in the North Hemisphere, and we can and the enhanced regional headly circulation in the South Hemisphere. This will provide more favorable environments for the TCs in the North Hemisphere and provide less And this will provide more favorable environments for TCs in the South Hemisphere and will provide less favorable environments for TCs in the North Hemisphere. And we can see the two GPI shows similar spatial patterns, and when only considering AA and GHG forcing, the GPI anomalies is much smaller than that of any individual forcings. And we hope this is that the AA and GHG forcing has comparable and opposite impacts on global TCs. By defining important index based upon the magnitude of GPI, we can see that the contributions from the AA is 50% for the global scale, North Hemisphere scale, and the basins. Further, the relative importance of factors from GPI are further assessed, and we can see the MPI and the PI and the vertical wind shear is the major contributors to the GPI change, and the vertical wind shear and the omega is a major contributor to the DGPI. Also, from the changes of surface turbulent fluxes, we can see two forcings are in a comparable magnitude over the North Hemisphere TC development zone. By further applying EOF analysis of GPI, we can see the similar. We can see the similar patterns, and the EOF results of EOF also showing the cancellation pattern between the two forcings, and the temporal evolution also shows consistent with the tropical and global and tropical mean SST, and also shows a competition between two leading models of two forcings lead to a weaker change in GPI during historical period, and the global and tropical mean SST implying that AA are more efficiently modulate TC environment. Lastly, we summarize this talk. And under AA forcing, there is a North Hemisphere decrease and a South Hemisphere increase GPI TC patterns. And it is mainly due to the SST gradient under AA forcing driving Hadley circulations and other associated circulations that shaping the global hemispherically asymmetric TC pattern. And AA and GHG forcing have the comparable and opposite impacts on global TCF. In terms of the AA's radiative forcing is only about 1 out of 3 of that from GHG, and we think that AA is more efficient in changing TC environment. Also, this study also provides us some implications. AA and GHG are both critical for regional TC frequency change and thus TC threats. And second, ambitious mitigation of anthropogenic emissions, especially for azoles, as the Paris Agreement could increase the North Hemisphere TC threat. That's all. Thank you.
So thank you very much for the presentation. I'd like to take some questions or comments from audience. Yes, please, Professor Emmanuel.
This is not really a question, it's a comment. I think what you've said is terribly important, and it's not really realized by people. When they talk about anthropogenic change, they're almost always referring to greenhouse gases, which are important. But the aerosols, just as you mentioned, even though the radiative forcing is 1/3, are much more effective at suppressing tropical cyclones because they're regional. And it's just the way you put it. There are more gradients associated. So I think nowhere is this more clear than in the Atlantic, when demonstrably the aerosols caused a drought of hurricanes in the 1980s, 70s, and 80s. And then the Clean Air Act, which reduced aerosols, have brought hurricanes back. A lot of journalists, a lot of people think that the big increase we've seen in Atlantic hurricanes has been because of global warming, whereas really they've been because of the cleaning up of the aerosols. That's my comment. You don't have to respond. Thank you for your talk.
Thank you.
So thank you very much. Any other questions or comments? No? Then may I ask one question? So what the relationship or the physical process are supposed between the anthropogenic, both anthropogenic aerosol and the greenhouse gases to the relationship with the environmental condition and the tropical cyclone activities. So you showed the statistical signals for the response about these greenhouse gases or the aerosol conditions, but also what kind of the physical processes or some mechanisms are supposed or assumed for these relationships found in this statistical analysis. It may be a little bit difficult to the response part one because here the students for just switch to present this about the content. So if you can, so no problem.
Can you please read?
Okay, so right there I will talk about you. Yeah. Okay, any other questions or comments? Nothing? So I would like to move on to the next presentation. Thank you very much.